Till now in semiconductor physics, we have discussed the basic concept of intrinsic semiconductor and extrinsic semiconductor. Now today we are going to see the most important concept of this semiconductor physics. Actually, now we will learn about the calculation of carrier concentration and Fermi level in semiconductors. As semiconductors, you know, are of two types, intrinsic and extrinsic semiconductor. So the same problem will be dealt for the intrinsic semiconductor and also for the extrinsic semiconductor. This first lecture is for the carrier concentration Fermi level for intrinsic semiconductor. Actually, the calculation is very vast, very lengthy. So, I would like to divide the calculation of carrier concentration and Fermi level for intrinsic semiconductor in two parts. And this is the first part of this lecture. Actually, in this first part of the lecture, we will see only the calculation of concentration of electrons in conduction band and concentration of holes in valence band. And after that, in second part of the same lecture, we will see the calculation of Fermi level or Fermi energy in case of intrinsic semiconductor. Okay? Actually, you know, when you talk about the carrier concentration, you know, in case of intrinsic semiconductor, there are two types of carriers, that is charge carriers, and those are electrons and holes. Electrons actually move in the conduction band and holes move in the valence band. Okay. So separately we will see how we can calculate the concentration of electrons and holes in conduction band and in valence band respectively. Okay. Since electrons and holes are fermions, they obey Fermi-Dirac statistics. So definitely, if you are talking about the concentration of electron and holes, you must follow the technique of Fermi-Dirac statistics, which we have learned in very detail in our course on statistical mechanics, and also in this solid state physics when you have studied the free electron theory of metals. Actually, the concentration of electron and holes in a semiconductor can be obtained from the knowledge of densities of available states in valence band and the conduction band, as well as the Fermi-Dirac distribution function. And the expression for the Fermi level or Fermi energy is then obtained from these carrier concentration. So there will be actually two mathematical tools. First one is density of states in valence band and conduction band, and another is Fermi-Dirac distribution function, which will be used for finding the carrier concentration of electron and holes both. Okay. So now let us start to know about the calculation of electron concentration in conduction band. Okay. First of all, I am not talking about the electron in conduction band, but we are talking about the free electron. Okay, just like electrons in a metal, in accordance with free electron theory of metals, you know that the electron the valence electron in a metal behaves like a free electron. Okay, and what will be the number of those free electrons in unit volume whose energy lies between E and E plus dE? Actually, this problem you have seen earlier in the statistical mechanics and also in case of free electron theory of metals. So the number of free electrons per unit volume in the energy range between E and E plus dE, you can remember this is given as dNE equal to G of E dE times F of E. Can you remember this formula? This result we have discussed in very detail in my playlist of statistical mechanics in the chapter Fermi-Dirac statistics. So if you have not watched that video till now, you must go through that video. Okay, I will suggest you. Here, this G of E dE, what is this? This is actually the density of states in the energy range between E and E plus dE. When you say density of states, what does it mean? It means this is the total number of allowed electronic states or allowed quantum states per unit volume in the energy range E and E plus dE. It means these are the quantum states in which electron will remain. Okay. And what is this F of E? This is the well-known Fermi-Dirac distribution function. And what does it mean? Actually, Fermi-Dirac distribution function is also known as occupation probability at energy E. It means this measures the probability that an electron will be found in the energy state E. And when you multiply by this occupation probability to the density of states, then you get the number of electrons or number of fermions in this energy range between E and E plus dE. So the number of electron whose energy lies between E and E plus dE, that is given by the product G of E dE times F of E. Okay. Now, you can also remember from my previous videos the expression for this G of E dE and F of E. You can remember. When you talk about this G of E dE, this is actually equal to 4 pi over h cube times 2m to the power 3 by 2 times e to the power half dE. Can you remember it? Definitely, if you have watched my video on statistical mechanics, then you can remember it. Okay. Actually, here m is the mass of free electron, not an electron inside a crystal, but a free electron. Okay. And the expression for this distribution function f of e, this is well known, and this is 1 over 1 plus e to the power e minus ef divided by kt. Okay, where you know this ef is what? This is the well known Fermi energy. Okay, or Fermi level you can also say. So these are the expressions for these two quantities, that is density of states G of E dE and the distribution function f of E or occupation probability f of E. So now you can put the values of G of E dE and f of E from equations A and B in this equation 1 to get the value of D and E, which is actually the number of free electrons per unit volume having energy between E and E plus dE. This is in this certain limit of energy, this much electron actually lies. Okay. So let us put it in equation 1. And then you will get this D and E equal to this much. This is 4 pi over h cube times 2m to the power 3 by 2 times e to the power half times 1 over 1 plus e to the power e minus ef over kt dE. Okay. Actually, till now we have talked only about the free electron. This is the mathematical tool, and this tool will be now applied to our present problem. Here our aim is to find the value of this D and E if the electrons are not free, but they are in the conduction band of a pure semiconductor. Okay. So there will be something different from this different value of some quantities in this if we are talking about the electrons in conduction band of the intrinsic semiconductor. So what will be the difference when we will apply this result to the electrons moving in conduction band? First of all, you can think this m is what? This is mass of a free electron, and you have already studied the concept of effective mass of electron. Whenever an electron is not free but it is inside a crystal, okay, then its mass is not equal to its free mass m, but then its mass is called effective mass. So definitely, if you will apply this equation 2 for the electrons in conduction band, this m should be replaced by the effective mass of the electron, which will be denoted by the symbol Me star. So this one will be the different from equation 2. Okay. Now again, this energy E, this is actually the kinetic energy. Why it is kinetic energy? Because when we talk about the free electron, then this E represents its total energy, and in case of free electron, since potential energy is 0, so E means what? E means kinetic energy. Okay? But here, when you talk about this E in the exponential factor, then it represents the total energy, not of free electron. Okay? So at both places, E has different meaning. When e to the power half is, as far as this e to the power half is concerned, this represents the kinetic energy of the electron. Okay? And you can see in conduction band, okay, the lowest value or the least value of energy of the electron is EC. Okay? And if you are talking about an electron like this, which I have shown here, and its total energy is E, okay, then E minus EC, that is this much, this will be the measure of kinetic energy. As you can see, I have mentioned it here, that in this upward direction, we note the kinetic energy. So actually, instead of E, now we will write E minus EC, which will represent the kinetic energy of the electron in this conduction band when its total energy is E. Okay? So you have to make two differences. M will be replaced by Me star, and this E on which the power is half, that will be replaced by E minus EC. Actually, EC is the energy of the electron in conduction band at the bottom of the conduction band. Okay? But we will not change this E, which is as a power on the exponential factor. Okay? So now, number of electrons in conduction band in unit volume of conduction band whose energy lies between E and E plus dE. What will be that? That will be now written like this. dNE symbol has been, I have taken same, and that will be 4 pi over h cube times 2Me star to the power 3 by 2. Mark it. Not M, but Me star now. And at the place of E, now I am writing E minus EC. Okay? But this E remains at each. Okay? So this is the number of electron per unit volume in the conduction band having energy between E and E plus dE. So I have mentioned it here. You can see it is evident from the figure that an electron occupying an energy state E in conduction band possesses kinetic energy E minus EC. Okay? Since the electron is inside the crystal, so the free electron mass M must be replaced by its effective mass Me star, and E should be replaced by E minus EC. Okay? And so this equation 2, which was for free electron, now for the electrons in conduction band becomes like this, which has been written in this equation 3. Okay? But this D and E represents only those electrons of conduction band whose energy lies between E and E plus DE. But our aim is to find the total number of electron in unit volume of the conduction band for the entire range of energy. And what will be the entire range of energy? You can see the lowest energy or the least energy of electron in this conduction band will be equal to EC, and the uppermost limit or the highest energy of electron will be simply infinity in accordance with the semi-classical theory. Okay? So if we will integrate this D and E between the limits E equal to EC and E equal to infinity, then you will get actually the number of electron per unit volume in conduction band, which is called concentration. Number of electron per unit volume is called concentration. So the concentration of electron in conduction band will be given like this: Ne equal to 4 pi over h cube times 2 me star to the power 3 by 2 integral from E equal to EC to E equal to infinity, E minus EC whole to the power half, and divided by 1 plus E to the power E minus EF over KT dE. Okay. Now actually this factor KT, where you know K is Boltzmann constant, at a temperature which is near about the room temperature, the KT has a value of 0.025 electron volt or 0.026 electron volt, you can say, because you know K is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. Okay, and when you talk about the room temperature, T is almost equal to 300 Kelvin. Okay, so when you will multiply it, then you will get the energy in joule, and when you will divide that value by 1.6 into 10 to the power minus 19, then you will get the energy in electron volt, and that will come out to be like 0.025 electron volt. Okay, so KT is this much. So actually for this value of KT, this exponential factor e to the power E minus EF by KT will be much greater than 1. Much greater than 1. Okay? And if it is much greater than 1, then what will be the value of this denominator? You can see, since this exponential factor in denominator is much greater than 1, so we can neglect this 1 in comparison to the exponential factor. And so this denominator 1 plus e to the power E minus EF over KT is almost equal to simply this exponential factor. Okay? So you can simplify this result, that is equation 4, taking this approximation. Okay? And so taking this approximation under account, you can write Ne is equal to 4 pi over h cube times 2 me star to the power 3 by 2 times integral EC to infinity E minus EC to the power half times E to the power minus E minus EF over KT d. Actually, when this factor will be in the place of numerator, then sign will become, the sign of power will be minus. Okay. Now actually we have to evaluate this integral for getting the value of Ne, which is electron concentration in conduction band. And for this we have to cast this integral into a proper form so that integration can be done. And for this we actually done a simple algebra. You can see in our original result there is e to the power minus E minus EF by KT. Okay? And here is a factor of E minus EC. So our aim is to raise this E minus EC as the power of this exponential. Okay, but when you will write it, this EF will be left and EC is extra, so you have to multiply this by E to the power EF minus EC. So when you will take the product of this exponential factor and this exponential factor, result will be just like previous, that is E to the power minus E minus EF by KT. Okay. But after this algebra, the integration will be done very easily. Okay. So now to evaluate this integral, we use the method of substitution. We will substitute this E minus EC by KT by a new variable, let us say x. So I have substituted here, you can see E minus EC divided by KT is equal to x. Or you can say that E minus EC is equal to KT times x. But in our equation, there is also dE, so you must find dE by taking the differential of this much. Since EC is constant, so its differential will be 0. So the differential of LHS is simply dE. And in RHS, again, KT is constant factor, so the differential will be only of x, which is dx. So dE is equal to KT times dx. Okay. Now check the limit. What will be the limits of the integration when you have used this new variable x? Okay. So let us see. When E is equal to EC, then what will be x? You can see. If this E is equal to EC, then E minus EC will be 0. So 0 will be equal to KT times x. And therefore you can say that x is 0. So for the limit E equal to EC, you have to write x equal to 0. Okay. And again you can see the upper limit is E equal to infinity. When you will take this E equal to infinity, you can see then in LHS there will be infinity, and that is equal to KT times x. So x will be infinity. So when E is infinity, then x is also infinity. So now in case of this new variable, limits will be 0 to infinity. At the place of EC, you will have to put 0, and infinity remains at edge. Okay. So now the result for NE will be what? This will be 4 pi over h cube times 2 ME star to the power 3 by 2 E to the power EF minus EC by KT. This factor is at edge. Okay. But inside the integral, you can see here there was E minus EC to the power half. But you can see E minus EC is KT times x. So this will be KT to the power half times x to the power half. And exponential factor was E to the power minus E minus EC by KT. But E minus EC by KT is x. So this will be E to the power minus x. And what is dE? You can see dE is KT dx. So at the place of dE, I have written KT times dx. Okay. Now you can see KT to the power half times KT. This will be KT to the power 3 by 2. And here 2 ME star has also power 3 by 2. So you can combine these two. So your result is 4 pi over h cube times 2 ME star KT to the power 3 by 2. Okay. And this exponential factor remains at edge, and inside the integral there is x to the power half times E to the power minus x dx. Actually, this is a very well-known standard integral, and its value is obtained by the use of gamma function. Okay. So if you have an idea of gamma function, which we study actually in mathematical physics, then you can say that the value of this integral is equal to pi over 4 to the power half, or pi to the power 1 by 2 over 2. Okay. So you can remember this value because this is a standard integral. So now let us replace this integral by this value. Okay. And after replacing, what will happen? You can see the result will now become Ne equal to 2 times 2 pi me star kt divided by h square whole to the power 3 by 2 times e to the power minus ec minus ef over kt. So this is actually our final result for the concentration of electron in conduction band. You can see this is number of electron per unit volume in conduction band. Okay. This is actually in terms of EC. In the second part of this lecture, we will also see this concentration in terms of EG, which is band gap. But in this first lecture, we are calculating Ne in terms of EC, which is actually the least energy of electron in conduction band, or the electron situated at the bottom of the conduction band. That electron has energy equal to EC. Okay, so mark this result. Okay, now actually we will recast this expression for concentration of electron in different form. Actually, you have seen earlier that the occupation probability, that is Fermi-Dirac distribution function for electron having energy E, is given as 1 over 1 plus e to the power E minus EF divided by KT. Actually here this Fe measures the probability of finding an electron in energy state E. Okay. So if I will ask you, can you find the probability of electron finding in energy state EC, then what will be that probability? That probability can be easily obtained by this result, simply replacing this E by EC. Okay. So you can say that the occupation probability of level EC is given like this: F of EC equal to 1 over 1 plus e to the power EC minus EF over KT. You can see here EC has been written at the place of E. But as you have seen earlier that this exponential factor is much greater than 1, so you can neglect this 1 in denominator, and neglecting it we find that this F of EC is equal to this much. And when you will bring it in at the place of numerator, then F of EC will be what? This will be e to the power minus EC minus EF by KT. Okay. So if your aim is to write down the expression for this concentration of electron in terms of this parameter F of EC, you can replace this exponential factor simply by this F of EC. So replacing in equation A1 that factor by F of EC, we get that Ne is equal to 2 times 2 pi me star kt over h square whole to the power 3 by 2 times F of EC. Okay, this is the carrier electron concentration in the conduction band, which has been defined in terms of this parameter F of EC. Actually, this F of EC is what? This is the occupation probability at the or you can say that this is the occupation probability at the energy EC. But you have seen earlier that whenever we find the number of electron in a particular energy range, then it is given by G of E dE times F of E. Okay. So here at the place of F of E, there is F of EC. Okay. And so this factor 2 times 2 pi me star kt divided by h square whole to the power 3 by 2, This is at the place of this density of states. So you can say that the first factor, that is 2 times of 2 pi me star kt divided by h square whole to the power 3 by 2, this first factor on RHS definitely will represent this density of states. Actually, it is called effective density of states of electrons at the conduction band edge. Why conduction band edge? Because EC is at the edge, bottommost edge of the conduction band. So, and we denote this density of states by the symbol Nc. And so that if you will replace this factor, first factor in RHS of equation A2 by Nc, which is actually the effective density of states of electrons at the conduction band edge, then the expression for Ne will become Nc times e to the power minus Ec minus Ef over Kt. Okay? Actually, as I have told you that this Nc is equal to this much. Okay? Now, you can see the expression for this Nc. Except this temperature T, all quantities appearing in this expression are universal constant. And so they will have particular values, and you know all those values. So if in case of silicon, we will put the value of Me star, K and H are universal constant, but Me star depends on the material, the electron belong to which parent crystal, that determines the effective mass. So if you are talking about the effective mass of electron in case of silicon, then the numerical value of all constants will be put here, and then it is found that Nc is equal to 2.8 into 10 to the power 25 times T divided by 300 whole to the power 3 by 2 per meter cube. Okay. So in this way you have seen that how applying the Fermi-Dirac ideas of Fermi-Dirac statistics, we can easily obtain the expression for the concentration of electron. And you can see this concentration of electron actually depends on this temperature T. Actually, with rise in temperature, the concentration of electron will increase, okay, exponentially. When we will talk about T equal to 0, then Ne will be equal to Nc times e to the power minus infinity, and that will be 0. So at 0 Kelvin temperature, there is no electron in conduction band, and this material behaves like an insulator. But as the temperature T is raised, the value of Ne increases exponentially. So with rise in temperature, electron concentration in conduction band increases. Okay. Now, our aim is to find the expression for the concentration of holes in valence band. Actually, on the same line, you can also find the expression for hole concentration in valence band. But how we can find it? For this, let us see a very important fact here. You know that the probability of finding an electron in energy state E is given by the Fermi-Dirac distribution function f of E. You know it. F of E means this is occupation probability, that is, it is the measure of probability of finding an electron in the energy state E. Okay? And what is a hole? You have studied earlier that hole is nothing, this is simply the vacancy created by the electron. Okay? Void created by the electron. Okay? So, if you want to know what will be the probability of finding a hole in the energy state E, then how we can find? Actually, this 1 minus f of E is the measure of probability of finding a hole in energy state E. But how? How you can say that this 1 minus f of E is the probability of finding a hole in the energy state E? Because this 1 minus Fe will be the measure of probability of an energy state E not to be occupied by the electron. Because f of E is the measure of probability of finding an electron in energy state E. So 1 minus f of, because probability has a maximum value of 1. So 1 minus f of E, that will measure the probability that electron is not in the energy state E. Okay? And if electron is not in the energy state E, then what is there? In that energy state, actually there is hole, because hole is the vacancy of electron. So these two statements are same. When you say probability of an energy state E not to be occupied by the electron and probability of finding a hole in the energy state E, both are same. You are talking about the same physical condition, because where there is no electron, there is hole. So this 1 minus f of E is the measure of probability of finding a hole in the energy state E. Okay? So when we will now try to find the concentration of hole, definitely in our calculation, this f of E, which was in the calculation of electron concentration, will be replaced by this 1 minus f of E. This will be the difference. Okay? So now let us see. You have seen that the number of holes per unit volume in the energy range between E and E plus dE. What will be this? This will be equal to density of states times the occupation probability for holes. But occupation probability for holes at energy E is 1 minus f of E, not f of E. You have just learnt it here. So the number of holes per unit volume having energy between E and E plus dE, which I have denoted by the symbol D and H, that will be equal to G of E dE times 1 minus f of E. Okay? Now, let us see what is this 1 minus f of E. You can easily find it because you know the expression for f of E. So this is 1 minus 1 over 1 plus e to the power e minus ef by kt. And when you will take the LCM and simplify, the result will be this much. This is e to the power e minus ef by kt over 1 plus e to the power e minus ef by kt. Okay? Now, situation here is just opposite to the situation of calculation of concentration of electron. Why? Because you can see holes are lying in this valence band and electrons are lying in this conduction band. Okay? And the highest energy of a hole in valence band is equal to EV. This is the uppermost level of the valence band. And in this downward direction, the kinetic energy of hole will increase. And so the lowest energy of the hole will be minus infinity. Mark it. Here the highest energy of electron was plus infinity and lowest energy of this hole will be minus infinity. Because as we move in the depth, the energy will become more and more negative. Okay? So actually in this case, the situation is just opposite to the situation of electron concentration calculation. Actually here, this factor e to the power e minus ef over kt. Here you know E will be definitely less than EF because In case of intrinsic semiconductor, you know, if this is valence band, this is conduction band, and Fermi level will be somewhere between these two bands. Okay, and you are talking about a hole in the valence band, and its energy is E. So you can see that this E is less than EF. Okay, and if E is less than EF, then E minus EF will be negative. So exponential has a negative power, and so this exponential factor will be much smaller than 1, much smaller than 1. And if exponential factor in denominator is much smaller than 1, then you should neglect this exponential factor in the denominator. Okay? Here the exponential factor will be neglected. And so this 1 minus f of e, that will be simply equal to e to the power e minus ef over kt. So you can see this is your 1 minus f of e. So in this way we have calculated the occupation probability of hole at energy level E. Okay. And now we will talk about the density of states. Okay. The well-known formula for density of states will be applied here after making again two differences. You know, the expression for g of e d is given as 4 pi over h cube times 2m to the power 3 by 2. But here we are talking about hole, so we must take the effective mass of hole at the place of m. So I have written here mh star, mark it. And here there was e to the power half. E was kinetic energy of the particle or the fermion. And here at the place of kinetic energy, what will be the value? You know, actually the probability of finding of holes decreases exponentially with increase in depth into the valence band, and also the kinetic energy of a hole in the energy state E in the valence band is EV minus E. Mark, you can see this band diagram that if we consider a hole here and its energy is E and energy at this level is EV, then this EV minus E will be the measure of the kinetic energy of the hole. So at the place of kinetic energy E, you must put EV minus E. Okay? And so this equation 7 measures the density of states for holes with energy E. And this equation 6 measures the occupation probability of hole at energy E. And when you will substitute the value of d of E, g of E dE and 1 minus f of E in this equation number 5, then you will get the number of holes in the energy range between E and E plus dE in the valence band. Okay, in per unit volume. So the number of holes per unit volume having energy between E and E plus dE, this will be given like this. This is 4 pi over h cube times 2mh star whole to the power 3 by 2 times EV minus E to the power half times E to the power E minus EF over KT dE. Okay. Yeah. This is the value of this one, 1 minus f of E. Okay. See. In this way, we have obtained the number of holes in unit volume whose energy lies between E and E plus D. Now, integrating this equation between the appropriate limit, we can actually find the total number of holes in unit volume of valence band. And how we can find it? You can see the energy E in valence band varies from minus infinity to EV. Okay, minus infinity to EV. So if you will integrate this equation, d and h between these two limits of E, then you will get the concentration of holes in valence band. And if that concentration is denoted by the symbol NH, then NH will be equal to 4 pi over h cube times 2 mh star whole to the power 3 by 2. Okay, and integral E from minus infinity to EV and EV minus e to the power half times e to the power e minus ef over kt d. Again, for integrating, we have to make a simple algebra. You can see at the place of this e minus ef over kt, I have written e to the power ev minus ef by kt times e to the power e minus ev by kt. You can multiply these two exponential factor, and after multiplication you will see that your result is this much. Okay, so the result remains unaltered. Now by method of substitution you can find the value of this integral, and for this we consider that this ev minus e over kt is equal to x. We consider it. So ev minus e is equal to ktx. Okay, and so minus de will be equal to kt dx, or de is equal to minus kt times dx. Okay, minus kt times dx. Okay, and now you can see what will be the limits for x. When E is equal to EV, then you can see when E is equal to EV, then from here you can see that x will be 0. And when E is equal to infinity, actually then this x will be E is equal to not infinity but minus infinity, E equal to minus infinity. So then x will be equal to plus infinity, because here there will be minus sign and minus minus will become plus, so x will be plus infinity. Okay, and so the expression for NH now you can write in this manner. This is 4 pi over h cube times 2 mh star whole to the power 3 by 2 e to the power ev minus ef by kt integral infinity to 0. And here there is actually ev minus e whole to the power half, but ev minus e you can see this is equal to ktx, so this will be kt to the power half times x to the power half, and here there is e to the power e minus ev by kt, but ev minus e by kt is x, so e minus ev by kt will be minus x, so this is e to the power minus x, and at the place of de we will write minus kt times dx. Okay, now you can see this kt to the power half and this kt will get multiplied, and that will be kt to the power 3 by 2, and so you can take it outside of the integral and your result is 4 pi over h cube times 2 mh star kt whole to the power 3 by 2. Okay, and this exponential factor is at each, and inside the integral there is x to the power half e to the power minus x dx. But due to this minus sign, you can omit this minus sign by interchanging the limits. This is the property of definite integral, that this minus will become plus if we will interchange the limits. So now limits are 0 to infinity. Okay, but you have seen earlier that the value of this integral is what? This is pi over 4 whole to the power half. Okay, so finally you get that NH is equal to 4 pi over h cube times 2 mh star kt whole to the power 3 by 2 e to the power ev minus ef by kt times pi by 4 to the power half. Okay. Now after simplification you can see that this nh is equal to this much, and this is actually the expression for the concentration of holes in valence band. This equation is analogous to the equation for concentration of electron, you can see. Okay. Only this exponential factor is different. At the place of me star there is mh star. These are the differences. Okay. Again you have learnt that the concentration is actually expressed in different forms. Okay. So when we will use the idea of f of E defined like this f of E, you know, this is actually the occupation probability. Okay. And you have also seen that this first factor is the measure of the effective value of density of a state at the valence band edge. Here valence band edge. So instead of that factor I have written here NB, this is just analogous to NC. So NH is equal to this much. You can write it. Okay. Where NB is equal to this much. Okay. And this NV is called effective density of holes at the valence band edge. Okay. Again, when you will find the value of 2 pi mh star k over h square whole to the power 3 by 2 and multiplied by 2, then for silicon it is found that NV is equal to 2.8 into 10 to the power 25 times T over 300 whole to the power 3 by 2. So you can see that concentration of electron, this is the value of NV. Okay. So the value of NV and the value of NC, this was NC or NE, what I have considered earlier. You can see this was considered NC. Okay. So NC and this NV both are equal for the this will be just okay. So the value of both of these factors NV and NC are equal. Okay. So I hope you have clearly understand the calculation of concentration of electron and concentration of hole. Okay. Thank you very much.